Good morning, class. My name is Jerome Donasco, your instructor today. So before we will proceed to our proper discussion, please arrange your chairs, sit properly, and pick up some pieces of papers. Okay, thank you. Okay, can somebody lead the prayer? Oh, Justin, can you lead the prayer? The Father, the Son, Holy Spirit. Dear Lord, let me do the right things. Let me say the right words. Let me hear no wrong. Guide me to the right ways and keep me safe from harms today. Dear Lord, Amen. Okay, sit. You may now sit. Thank you. Thank you, class. I will check your attendance. So, say present if your name is called. Thank you. So, all of you are present today. So before we start our lesson proper, let us have first a puzzle game. Do you remember our game yesterday? So we will have our game today, a new game called puzzle game. Okay, class. This is our puzzle game. So there are 4 words you can find in our puzzle. So you may now start finding our puzzle, our words, our 4 words for today. Okay. Okay, it's already time, so kindly state your first word here. Okay, modular. Correct. Modular. So, we have modular. Next word is arithmetic. Correct, arithmetic. Here is our word arithmetic. Arithmetic. Our third word, we have divisibility. Okay, correct. We have divisibility. It is a long word. Divisibility. Next is theorem. Correct. We have word okay. That is our 4 words in our 4-word puzzle class. Thank you. Do you have now an idea of what is our lesson today? Okay. But before that, Amorin, what is our lesson yesterday? Correct. Our lesson yesterday is about Euler's 5 function. So what is Euler's 5 function, by the way? So, Euler's 5 function is derived from originated from Leonhard Euler, which is born on April 15, 1707 in Switzerland. So, history of Euler's 5 function. So, Leonhard Euler introduced the function in 1763. However, he did not at that time choose any specific symbol to denote it. In a 1784 publication, Euler studied the function further, choosing the Greek letter pi to denote it. He wrote pi d for the multitude of numbers less than b and which have no common divisor with it. So, the definition varies from the current definition for the totient function at t equals 1 but is otherwise the same. So the now standard notation of phi comes from Gauss in 1801 treatise Disquisitiones Arithmeticae. Although Gauss didn't use parentheses around the argument and wrote phi, thus it often called Euler's phi function or simply the phi function. So before that is our lesson yesterday. So our lesson today is about modular arithmetic, divisibility and modular arithmetic. Okay. Here is our objectives. Here's our objective class. Okay. So altogether, objectives. At the end of the lesson, the students are able to define divisibility and modular arithmetic, solve the division algorithm, and show appreciation on the importance of application of Carl Friedrich Gauss in solving real-life problems. We will have our group activity, but before that, I will ask somebody based on his or her own understanding. So, what is modular arithmetic? Okay, Justin. Okay, nice idea. Another one? Maureen. Okay, good. Very good. So, you have some backgrounds about the modular arithmetic. But, so before, I will group you into two groups. So, this row over here and from the left row and to the right row. So these are your groups. So group 1 and group 2. So I have given equation here. So direction, answer the following. Write integer, so big letter integer, integer is the quotient if the quotient is an integer. So write integer if the quotient is an integer. And write not, big letter, not, if the quotient is not an integer. So for the group 1, 15 divide 3. Number 1. Number 2 is 16 divide 5. Number 3 is 20 divide 4. Then 18 divide sa group for the group 2, 18 divide 3. Number 2 is 35 divide 3. Number 3 is 40 divide 5. So, you can answer it on a single piece of paper. And for the group who will finish first is you have some an extra point. So, you may start now. Okay, group 2 finish first, so you have an extra point. So I will add group 2 plus 2 points. So if you got it correct, so each of the item is 5 points. So 5 points, 5 points, 5 points. So 5 plus 5 plus 5. So plus 2, so you will have 17 points. You will be given 5 points, and for the group 1, for the participation, so you will be given plus 3 points, to be fair. So group 1, so the answer, what is your answer? Okay, 15 divide 3 with okay. Sorry for that, ha. So 15 divide 3, the answer is 5. Our answer is 5. So, 5, integer or not? An integer. Okay. If your answer is integer, you have 5 points. 5 points for group 1. So, 16 divide 5. The answer is 3.2. So the answer is 3.2. So this is not an integer. If your answer is not, so you have 5 points. Number 3. 20 divide 4. The answer is 5. So this is an integer. If you answer integer, you have 5 points for group 1. So 5 plus 5 plus 5, 15 plus 3, 18. So, you have 18 points, group 1. Not bad. So, for group 2, 18 divide 5. Your answer is 18 divide 3. So, your answer is 6. An integer. So, if your answer is integer, you have 5 points. So, 35 divide 3. 35 divide 3, the answer is 11.66. So, this is not an integer. So, your answer is not. So, if your answer is not, so you have 5 points. So, 40 divide 5. The answer is 8. So, 8 is an integer. So if you answer integer, you have 5 points. So 5 plus 5 plus 5 plus 5 with your group 2 has 20 points. So that's correct. Okay. Diba yesterday I have given you reports, your given reports. So you may now present it today. So I have some guide questions for your reports, di ba? We have divisibility and modular arithmetic. So, first is, what is division? Okay, from the divisibility and modular arithmetic, division is when one integer is divided by a second non-zero integer, the quotient may or may not be an integer. For example, 12 divide 3 equals 4 is an integer. So that is our activity for the day. So where areas 11 divide 4 equals 2.375 is not an integer. So if a and b are integers with a is not equal to 0, we say that a divides b if there is an integer c such that b equals ac, or equivalently if b over a is an integer. When a divides b, we say that a is a factor or divisor of b, and that b is a multiple of a. The notation a is equivalent to b denotes that a divides b. We write a is not divides when a does not divide b. So we can express a divide b using quantifiers as element c, ac equals b, where the universe of this course is the set of integers. So we have some examples here. Determine whether 3 divides 7 and whether 3 divides 12. So we see that 3 divides 7 because 7 is divide 3 is not an integer. So on the other hand, 3 divide 12 because 12 divide 3 equals 4. So example 2. Let n be positive integers. How many positive integers not exceeding n are divisible by d? Solution. The positive integers divisible by d are all the integers of the form dk, where k is a positive integer. Hence, the number of positive integers divisible by d that do not exceed n equals the number of integers k with 0 greater than dk, a less than dk is not less than n or with a less than k, greater than k. Therefore, there are n d over d positive integers not exceeding n that are divisible by d. So, theorem number 1, we have here. So, let a, b, and c be integers where a is not equal to 0 then. If a divide b and a divide c, then a divide b plus c. If a divide b, then a divide b and c for all integers c. If a divide b and b divide c, then a divide c. Will we give a direct proof of number 1? Suppose that a and b and a divide c, then from the definition of divisibility, it follows that there are integers and t, s and t with b equals a and s, and c equals a and t. Hence, b plus c equals as plus at equals a s plus t. Therefore, a divides b plus c. So what is division algorithm? So division algorithm is when an integer is divided by a positive integer. There is a quotient and a remainder as the division algorithm shows. Theorem number 2. The division algorithm. Let a be an integer and b a positive integer. Then there are unique integers q and r with 0. It's not greater than r and not greater than b, such that a equals dq plus r. Definition 2. In the equality given in the division algorithm, d is called the divisor, a is called the dividend, q is called the quotient, and r is called the remainder. This notation is used to express the quotient and remainder q equals a div d, and the remainder of r equals a mod d. Okay. Example, what are the quotient and remainder when 100 is divided by 11? So solution, we have 101 equals 1 times 9 plus 2. Hence that the quotient when 100 is divided by 11 is 9 equals 101 div 11. And the remainder is 2 equals 100 mod 11. So that is our theorem 2. So what is modular arithmetic, by the way? If a and b are integers and m is a positive integer, then a is congruent to b modulo m if m divides a minus b. We use the notation a is equivalent b to b mod m to indicate that a is congruent to modulo m. We say that a is congruent b parenthesis mod m is congruence, and that m is its modulus plural moduli. If a and b are not congruent modulo m, we write a is not congruent b or mod m. So theorem 3, let a and b be integers and let m be a positive integer. Then a is congruent to b mod m if and only if a mod m is equal to b mod m. So, example, determine whether 17 is congruent to 5 modulo 6 and whether 24 and 14 are congruent modulo 6. Solution. Because 6 divides 17 minus 5 equals 12, we see that 17 is congruent to b 5 mod 6. However, because 24 minus 14 equals 10 is not divisible by 6, we see that 24 is not congruent to 14 or mod 6. So, this, the Greek mathematician Carl Friedrich Gauss developed the concept of congruence at the end of the 18th century. The notation of congruences has played an important role in the development of number theory. So, big thanks to mathematician Carl Friedrich Gauss. Our theorem number 4. Let m be a positive integer. The integers is A and B are congruent modulo n if and only if there is an integer k such that A equals B plus km. Theorem 5. Let m be a positive integer if A is congruent to B mod m and C congruent to D mod m. Then A plus C equal A congruent to B plus D mod m and AC congruent to BD mod m. So we have corollary. Let m be a positive integer and let A and B integers. Then parenthesis A plus B mod m is equal to parenthesis of A mod m plus B mod m or mod m and AB mod m equals parenthesis of A mod m times B mod m and mod m. So activity. So that is our the divisibility, the modular arithmetic, and our division algorithm. Okay. Do you understand, class? Do you understand our reports? Our lesson today, the definition about the division algorithm, and the modular arithmetic. Okay. We will have now our another activity, so group activity. But before that, kindly loosen up. So kindly stand up. So we will have our exercise today. Our math exercise. This is very unique, uncommon exercise, uncommon dance. Okay. Are you familiar with Chikanding? That is our not today. Our exercise. Chikading, palipat, lipat. Chikading, pasaya, lipat. Chikading, palipat, lipat. Chikading, palipat, lipat. Saka chikading, lumapo sa sanga. Pumapay ang isa, dalawa na sila. Chikading, palipat, lipat. Chikading, palipat, lipat. Chikading, malubapo sa sanga. Dumating ang isa, tatlo na sila. Chikading, palipat, lipat. Chikading, pasaya, lipat. Chikading, malubapo sa sanga. Dumating ang isa, dapat na sila. Chikading, palipat, lipat. Chikading, pasaya, lipat. Dapat ng chikading na dumapo sa sanga. Dumating ang isa, lima na sila. Chikading, palipat, lipat. Chikading, palipat, lipat. Limang chikading na dumapo sa sanga. Umalis ang isa at na sila. Chikading, palipat, lipat. Chikading, palipat, lipat. Dapat ng chikading na dumapo sa sanga. Umalis ang isa, tatlo na sila. Chikading, palipat, lipat. Chikading, palipat, lipat. Dapat ng chikading na dumapo sa sanga. Umalis ang isa, dalawa na sila. Chikading, palipat, lipat. Chikading, palipat, lipat. Dapat ng chikading na dumapo sa sanga. Umalis ang isa, na sila. Chikading, palipat, lipat. Chikading, palipat, lipat. And thank you, class, for your participation. So you may now sit properly. Arrange your chairs. Kindly. So answer the following division algorithm and modular arithmetic. For number 1, we have 58 is divided by 7. For number 2, we have 89 is divided by 9. For number 3, we have 356 is divided by 15. Number 4, we have 901 is divided by 19. Number 5, we have 288 is divided by 29. I will give you 5 points each number if you got it correct. So your time starts now. We finish answering their activity today. So let us answer number 1. So 58 is divided by 7. So first we'll get our quotient. So 58 divided 7, the answer is 8. Without you don't need to put the remainder first. So you need to put the quotient. So our answer is 8. So 8 equals 58 div 7. Next is our remainder. So 8 times 7, the answer is 56. So 58 minus 56, the remainder is 2. We have the remainder 2. So 2 equals 58 divide 7. That is our answer for number 1. So 89 is divided by 9. So 89 is divided by 9. So 89 divided 9, our answer is 9. We have 9. 9 equals 89 div. By the way, this is mod. This is mod. So div 9. And 9 times 9, our answer is 81. 81. Am I correct? 81. So 81, 89 minus 81, the answer is 8. So 8 equals 89 mod 9. So next is 356 is divided by 15. So 356 is divided by 15. So the answer is 23. So 23 equals 356 div 15. So 23 times 15, then the answer, you need to minus 356 by the answer of 23 times 15, and you will get the answer of 11. So 11 equals 356 mod 15. Number 4. So 901 is divided by 19. So 901 divided 19, the answer is 47. 47 equals 901 div 19. So 47 times 19, then 901 minus the answer of 47 times 19. So our answer is 8. So 8 equals 901 mod 19. Number 5, our last number. So 288 is divided by 29. 288 divide 29. The answer is 9. Equals 288 div 29. So 9 times 29, then 288 minus the answer of 9 times 29. So our answer is 27. We have 27. So 27, 280 equals 288 mod 29. So if you got correct, you have 5 points. 5 points. 5 points. 5 points. And 5 points. So all in all, with 5, 10, 15, 20, 25, you got 25 points all in all. Okay. For evaluation, individual. Solve the given division algorithm in modular arithmetic. Give the quotient and remainder of the following. So you need to identify which is the quotient, and which is the remainder of the following answer of our given activity of division algorithm and modular arithmetic. So for number 1, we have 76 is divided by 3. Number 2 is 57 is divided by 9. Number 3 is 100 is divided by 10. Number 4, we have 90 is divided by 4. And for number 5, we have 178 is divided by 4. So your time starts now. We'll give you 5 minutes to answer this. And after that, we will give you an assignment for tomorrow. Answer number 1. So 76 divided by 3. So 76 divided by 3, the answer is 25. 25 equals 76 give 3. And 25 times 3, so 76 minus 25 times 3, the answer of 25 times 3. So we have 176 mod 3. This is our quotient, and this is our remainder. 57 is divided by 9. So 57 divided by 9, the answer is 6. We have 6 equals 57 div 9. This is our quotient. Okay. And 57 minus the answer of 6 times 9. So the answer is 3. 3 equals 57 divide 9. This is our remainder. Number 3. 100 is divided by 10. 100 is divided by 10. The answer is 10. So 10 equals 100 div 10. This is our quotient. Quotient then. 10 times 10. The answer is 100. So 100 minus 100. We have 0 quotient. So 0, 100 mod 10. The answer, that is our remainder. So number 4, 90 is divided by 4. So 90 divided by 4, the answer is 20. The answer is 22. Equals 90 div 4. That is our remainder. Then 90 minus the answer of 22 times 4. So our mod is 2 equals 90 div mod 4. This is our quotient rather, and this is our remainder. Then 178 is divided by 4. So the answer is 44. 178 div 4. This is our quotient. Then the 44 times 4, so 178 minus the answer of 44 times 4, our answer is 2. So 2 equals 178 mod 4. This is mod 4. This is our remainder. Again, wait. This is 10 points, 10 points, 10 points, 10 points, and 10 points. So 10 plus 10 plus 10 plus 10 plus 10, so on. 10, 20, 24. You have 5 points if you all got correct. So this is our evaluation technique. Okay, assignment, give at least 2 examples of theorem 4 and theorem 5. And class, you may now leave and dismiss. Thank you.